All right, finally we can talk about thiols here. So while there is a little bit to talk about in terms of reactivity, the most characteristic thing of thiols is their strong smell. Now, how do we make them? So we can do them by an SN2 reaction. That is probably the easiest way. You just take SH minus and alkyl halide, and that'll do an SN2 reaction to form a thiol. The only problem with that reaction is that often that reaction will actually occur twice. And so you end up with a thioether. So if you want to make a thiol, it's usually better to use what's known as a thiourea. So a thiourea is a thiol sulfur version of a functional group. And we're going to introduce three new functional groups here. We have the carbonate, the carbamate, and urea. So a carbonate is a carbonyl that has OR groups on both sides, or basically an ester with a second oxygen group. A carbamate replaces one of those oxygen groups with a nitrogen group. And a urea is when we have two nitrogen groups bonded to the carbonyl. So then a thiourea is a urea, but where we've replaced that oxygen with a sulfur. And so if we add thiourea itself to an alkyl halide, this lone pair on sulfur will do an SN2 reaction and kick out the iodine. At this point, we now have a sulfur cation. And because that sulfur is a cation, it's no longer nucleophilic. And so we don't end up with a second alkyl group on the sulfur. The reaction stops here. From here, we add sodium hydroxide to it. And sodium hydroxide will cleave the urea group, and we end up with a thiol. So in terms of reactions of thiols, there's really one critical reaction of thiols. And that reaction is the following. Is that we can take any thiol, and if we oxidize it, and if we were doing this in the lab, we might use something like iodine, and that thiol gets converted into a disulfide. The disulfide can go back the other direction by a reduction reaction, often using something like zinc and acid. So what is the importance of this reaction? Well, the place where this reaction is most important is biologically. If we talk about proteins and protein structure, proteins have what we call 4 different levels of structure, and we can see them here. Primary, secondary, tertiary, and quaternary. The primary structure is just the sequence of the amino acids, whatever amino acids are contained in that protein in the order that they're in. The secondary structure, as well as the tertiary structure, is how that chain of amino acids folds up into specific shapes. And then the quaternary structure is the interaction of more than one chain. But this reaction involving disulfides is really important in the secondary and tertiary structure, because the overall shape of a protein is determined by four things. If we think about all of our different amino acids, different amino acids will allow every amino acid has the basic structure of this. It's a carbon with an amine, carboxylic acid, a hydrogen, and some sort of R group. And how that amino acid functions is based on what the R group is. And so the folding of the protein chain is done through the attraction of amino acids that are not next to each other. Now, in the case of where the R groups are nonpolar, we get a van der Waals attraction. If we have things like alcohols and amines, we can get hydrogen bonding. And between some of the ionic R groups, we can get salt bridge. But all of these are intermolecular forces. There's only one situation where non-consecutive amino acids will form an actual covalent bond, and that's through the disulfide bonds formed by the side chains on cysteines. And so this reaction, the thiol going to the disulfide or the disulfide going to the thiol, plays a major role in protein shape. And one of the best examples of that, again, this is going to be when we are looking at cysteine. Cysteine has this structure. So most proteins have about, a little less than 3% cysteine. But one specific protein, keratin, has almost 3 times that. It's made up of 8% cysteine. And keratin, of course, makes up, a lot of our hair. And so in fact, the structure, the shape of your hair is largely controlled by where the disulfide bonds are. So if you have 2 cysteine residues and you oxidize them, then you form this disulfide bond, and that helps shape the molecule. So if you think about wanting to change how curly your hair is, what you're really doing is you're looking at these disulfide bonds in the keratin. If you want to change it, you apply some sort of reducing agent. So if you reduce them all, then you can break all of those disulfide bonds. Then you can rearrange it however you actually want it to be, and then you apply some sort of oxidant, and then you form a new set of disulfide bonds.